Space contains invisible boundaries that trap everything forever. Cross one of these lines and nothing can ever return. Not spaceships, not light itself, nothing. You probably think space is completely open. You can travel in any direction you want. That feeling breaks down at these cosmic barriers. Tonight we're discovering how the universe creates perfect traps. Why even the fastest things get caught forever. And what these boundaries reveal about reality itself. Before we explore these cosmic prisons, drop a comment about where you're listening from. If you enjoy these physics explorations, consider subscribing. These journeys into extreme science are meant to be shared. Scientists used to believe light could escape from anywhere in space. Light moves faster than anything else in the universe. Nothing seemed capable of trapping it permanently. Then astronomers discovered something impossible. Around certain massive objects in space, gravity becomes so strong it bends reality. Every possible escape route curves back inward. No path leads to freedom. This isn't about weak rocket engines or running out of fuel. Even light traveling at maximum speed cannot break free from these regions. The universe has created perfect cosmic prisons. Matter falls across this invisible boundary and disappears forever. Scientists call this point of no return an event horizon. That's the technical term for a one-way passage you can never reverse. Once something crosses this line, it's gone from our universe forever. 2 centuries before Einstein, Newton's simple math revealed something disturbing about gravity. The equations contained a prediction that seemed impossible at the time. Here's what Newton's numbers showed. Every object in space has an escape velocity. That's the minimum speed needed to break free from its gravitational pull. Make an object more massive while shrinking it smaller. The required escape velocity keeps climbing higher. Eventually, the escape velocity reaches 186,000 miles per second. That's exactly the speed of light. Newton's equations suggested some objects could become so gravitationally powerful that light itself couldn't escape them. These objects would be completely invisible. You could only detect them by watching how they affect nearby matter with their gravity. Classical physics had accidentally predicted black holes centuries before anyone understood what they meant. Einstein revealed why Newton's prediction actually works. Space and time aren't separate things. They're woven together into a single fabric that can be bent and stretched. Massive objects warp this space-time fabric like heavy balls pressing down on a trampoline. The more massive the object, the deeper the curve it creates. Light always travels in straight lines through this curved space. Near extremely massive objects, the space-time curve becomes so steep that straight lines loop back on themselves. Light tries to travel in a straight line, but the curved space forces it in circles. Every direction leads back toward the massive object. This creates regions where the space-time curve becomes so extreme that nothing can climb back out. The curvature forms a point of no return where all paths lead inward. Einstein's equations showed that the universe can literally trap light using geometry alone. A German physicist named Karl Schwarzschild solved Einstein's equations during World War I. His math revealed exactly where these cosmic boundaries form around any massive object. Schwarzschild discovered a critical radius that depends only on mass. Pack enough matter inside this radius, and space-time curves beyond the point of no return. The boundary forms at this precise distance from the center. For our Sun, this critical radius would be about 2 miles. That means if you somehow compressed our entire Sun down to a ball only 4 miles wide, it would create one of these cosmic traps. Everything within 2 miles of its center could never escape. The Schwarzschild radius gives us the exact mathematical location of the point of no return. It's not fuzzy or approximate. The boundary exists at this precise distance, creating the sharpest division in all of physics between escape and permanent capture. These cosmic boundaries don't just trap matter and energy. They create something even more fundamental, a complete separation of information between inside and outside. Think of information as any signal or message. Normally, information can flow freely throughout the universe. You can send radio signals to distant galaxies. Light carries information across cosmic distances. Communication works in both directions. These boundaries break that rule completely. Information can flow from outside to inside. But absolutely nothing can carry information from inside back to outside. The boundary creates a permanent information barrier. This makes these cosmic boundaries the most absolute barriers that physics allows. They don't just prevent physical escape. They cut off all communication between inside and outside forever. The universe has created regions that become completely isolated from everything else that exists. The bigger the monster, the bigger its cage. Black holes follow this simple rule with mathematical precision. Double the mass and you double the size of the boundary that traps everything forever. This relationship shocked scientists when they first calculated. Most objects in physics don't work this way. Make something twice as heavy and it usually gets denser, not bigger. But black hole boundaries expand in direct proportion to their mass. A black hole with the mass of our Sun creates a boundary about 4 miles wide. Pack in twice that mass and the boundary grows to 8 miles. 10 times the mass means 40 miles across. The universe scales these cosmic prisons with perfect mathematical consistency. This proportional relationship means the most massive black holes create the largest inescapable regions in space. Some contain billions of times our Sun's mass and stretch across distances larger than our entire solar system. Picture a perfect sphere floating in space. Nothing gets through this invisible shell. Everything inside stays trapped forever. Everything outside remains free to escape. Black hole boundaries form these perfect spherical shells around their centers. The sphere completely surrounds what scientists call a singularity. That's the technical term for a point where matter gets crushed toward infinite density, and the laws of physics may break down. This spherical boundary acts like a one-way membrane. Matter and light can pass through from outside to inside, but nothing can travel from inside back to outside. The sphere creates the most perfect isolation possible in physics. The boundary maintains this perfect spherical shape because gravity pulls equally in all directions from the central point. No matter which direction you approach from, you encounter the same inescapable barrier at exactly the same distance from the center. Your feet would experience crushing force while your head floated weightlessly. This impossible situation happens near these cosmic boundaries because gravity changes dramatically over short distances. Scientists call this deadly stretching effect spaghettification. The technical term describes how tidal forces tear objects apart when they approach the boundary. Your feet get pulled much harder than your head because they're slightly closer to the massive center. The difference becomes extreme near the boundary. Gravity at your feet might be thousands of times stronger than at your head. This difference stretches your body like taffy until the atomic bonds holding you together simply snap. For smaller black holes, spaghettification kills you long before you reach the boundary. Larger black holes allow you to cross the boundary intact, but the stretching still destroys you eventually as you fall toward the center. Rotation changes everything about these cosmic boundaries. A spinning black hole doesn't create a perfect sphere. Instead, it forms an egg-shaped boundary that bulges at the middle and flattens at the poles. The faster the rotation, the more distorted the boundary becomes. At extreme rotation, the boundary can become noticeably wider at the equator than it is from pole to pole. The spinning motion literally drags space and time around with it. This rotation creates a region outside the boundary where nothing can remain stationary. Scientists call this the ergosphere. Even if you fire your rockets at maximum power, the spinning space-time drags you around the black hole like a cosmic whirlpool. Angular momentum determines how much the boundary gets stretched. That's the scientific term for rotational energy that gets conserved. The more angular momentum a black hole has, the more its boundary departs from a perfect sphere. What if a black hole carried electric charge like a giant battery? The mathematics predicts something bizarre. Instead of one boundary, you get two nested spherical shells with a gap between them. These electrically charged black holes probably don't exist in nature. Stars contain equal amounts of positive and negative charge, so they stay electrically neutral when they collapse. But the theoretical possibility reveals how electric force competes with gravity near these boundaries. The outer boundary works like a normal black hole boundary. Cross it and you can never return to the outside universe. But between the outer and inner boundaries, strange physics takes over. Electric force partially cancels gravity's pull. Scientists call this theoretical object a Reissner-Nordström black hole. That's the technical name for the mathematical solution that describes charged black holes. The double boundary structure shows how electric force can modify the geometry of space-time itself. Light cannot move forward or backward at these cosmic boundaries. It gets frozen in place forever. This impossible situation happens because of how extreme gravity bends the paths that light must follow through space. Scientists call these light paths null geodesics. That's the technical term for the routes that light takes when traveling through curved spacetime. Normal space allows light to move freely in any direction. But near massive objects, these paths get twisted into impossible shapes. At the boundaries, something extraordinary occurs. The light paths become so curved that they loop back on themselves. Light tries to escape but ends up traveling in circles around the boundary. It neither falls inward nor escapes outward. This creates a critical surface where light gets permanently trapped. The boundary exists precisely where null geodesics can no longer lead to the outside universe. Mathematics defines the point of no return as the place where light paths lose all connection to distant space. Sophisticated mathematics reveals exactly where these boundaries form by tracking what happens to time itself. Near massive objects, the mathematical description of time behaves strangely. At the boundary, something remarkable occurs with time's mathematical representation. Physicists use mathematical tools called killing vectors to describe symmetries in space-time. The time direction killing vector represents how time flows in different regions around a massive object. This vector has a specific strength at every point in space. At the boundary, this time direction vector becomes null. That's a mathematical term meaning the vector loses all its strength and points nowhere. The mathematical description of time itself breaks down at this precise location. This nullification marks the exact position of the boundary. The mathematics shows that when time's directional vector becomes null, you've found the point where escape becomes impossible. The boundary exists where time's mathematical flow can no longer connect inside to outside. These cosmic boundaries create a permanent division in the causal structure of the universe. Scientists have developed a special type of diagram that shows exactly how information and signals can flow between different regions of space-time. Penrose diagrams compress infinite space and time onto finite pictures. These mathematical maps show every possible path that light or information can take throughout the universe. The diagrams reveal which regions can communicate with each other and which remain forever isolated. On these diagrams, the boundary appears as a diagonal line that stretches to future infinity. This line represents the absolute limit of causal connection. Nothing from below this line can ever send signals to regions above it. The diagrams prove that boundaries create permanent causal isolation. They divide the universe into regions that can never exchange information. The mathematical structure shows that these divisions are built into the fabric of space-time itself. You might expect infinite gravitational acceleration at these cosmic boundaries. Instead, something counterintuitive happens. The surface gravity remains perfectly finite, even though the boundary creates infinite consequences for anyone who crosses it. Surface gravity measures the gravitational acceleration that a stationary observer would experience right at the boundary. This quantity stays finite and depends only on the mass and size of the black hole. Larger black holes actually have smaller surface gravity. This finite surface gravity connects directly to temperature. The boundary radiates thermal energy at a temperature proportional to its surface gravity. Smaller black holes with higher surface gravity radiate at higher temperatures than larger ones. The mathematics reveals that finite surface gravity creates infinite redshift for outside observers. Light trying to escape from near the boundary gets stretched to infinite wavelength. This infinite stretching comes from finite surface gravity acting over infinite time. Can these cosmic boundaries ever shrink? The mathematics provides a definitive answer. Under normal physical processes, the area of a boundary can never decrease. It can only stay the same or grow larger. This area increase law works like thermodynamics. When black holes merge together, the final boundary area always exceeds the sum of the original areas. When matter falls across a boundary, the area increases further. No known physical process can reduce the total area. The law holds even for the most violent events in the universe. Two black holes can collide and merge in the most energetic explosions possible. The resulting boundary area still obeys the increased law with mathematical precision. This theorem reveals something profound about information and entropy. The boundary area measures the maximum information that can be hidden from the outside universe. The area increase law means the universe's hidden information can only grow, never shrink. Time stops completely at these cosmic boundaries. At least, that's what you see if you watch from a safe distance. An astronaut falling toward the boundary appears to freeze in place and glow red as time stretches to infinity. This happens because gravity affects the flow of time itself. The stronger the gravity, the slower time moves. Near the boundary, time slows down so much that it nearly stops compared to distant observers. You watch the falling astronaut's clock tick slower and slower. Their movements become sluggish. Their light shifts toward red as gravity stretches each photon. Eventually, they appear completely motionless, glowing faintly red against the darkness. From your distant perspective, the astronaut never actually crosses the boundary. They remain frozen at that position forever. Their image gradually fades as the light gets redshifted beyond detection. The astronaut becomes invisible but never seems to disappear inside. Everything feels perfectly normal as you fall toward the boundary. You might expect to hit some kind of wall or feel a sudden change. Instead, you pass through the boundary without noticing anything special happening. Your watch ticks at its normal rate. Your body feels no unusual forces. The boundary itself remains completely invisible as you cross it. Nothing marks this moment as the point of no return from your perspective. This happens because all of space-time falls with you. You and everything around you experience the same gravitational effects. Since you're in free fall, you feel weightless just like astronauts on the space station. The boundary only appears special to outside observers. From your falling reference frame, it's just another location in space. You cross it naturally and continue falling toward the center, unaware that you can never return to the outside universe. The entire future of the universe unfolds before your eyes as you fall. Stars evolve and die in seconds. Galaxies collide and merge. The cosmos ages billions of years while you experience only minutes. This acceleration happens because of gravitational time dilation working in reverse. While outside observers see your time slow down, you see their time speed up dramatically. Their fast-moving clocks appear to run at incredible speeds. Light from the outside universe gets blue-shifted as you fall. That means the wavelengths get compressed and carry more energy. This blue-shifted light brings you information about events happening at accelerated rates in the external cosmos. You witness the universe's entire future compressed into your final moments. The cosmic microwave background radiation glows brighter and hotter. Stars burn through their fuel rapidly. You see how the universe ends before you reach the center of the black hole. Mathematics reveals an unsettling truth about these boundaries. The same physical event produces completely contradictory descriptions depending on which coordinate system you choose to use. Coordinate systems are mathematical frameworks for describing positions and times in space. Think of them like different ways to make maps of the same territory. Each system can give accurate measurements but emphasize different aspects of reality. Schwarzschild coordinates make the boundary look like an infinite barrier where time stops. Kruskal coordinates make the same boundary appear perfectly smooth and crossable. Both descriptions are mathematically correct for the same physical situation. This coordinate dependence shows that only proper time matters physically. That's the time measured by clocks carried by actual observers. Different observers experience different proper times, which explains why they see contradictory versions of the same events. Can information travel both ways across these cosmic boundaries? The answer reveals one of physics' most fundamental asymmetries. Information flows easily from outside to inside, but cannot make the return journey under any circumstances. Information includes any signal, message, or data that can be transmitted. Radio waves, light beams, and particle streams all carry information. In normal space, information transmission works both ways between any two locations. The boundary breaks this symmetry completely. Signals from outside can reach someone who has crossed to the inside. But anyone inside cannot send any signal back to the outside universe. The boundary acts like a one-way information membrane. This creates the ultimate communication barrier. Once you cross the boundary, you become permanently isolated from the rest of the universe. You can still receive final messages from outside, but you can never respond or send information back. Can information be permanently destroyed in our universe? This question triggers one of physics' deepest crises. Black holes seem to violate a fundamental law that information must always be preserved somewhere. Here's the problem that keeps physicists awake at night. Throw a book into a black hole and all its information crosses the boundary. The words, pages, and ideas become trapped forever. Later, the black hole evaporates through quantum radiation and disappears completely. What happened to the book's information? Quantum mechanics says information can never be destroyed. It can be scrambled or hidden but must exist somewhere. However, the evaporating radiation appears completely random with no trace of the original book. This creates an impossible situation. Either information gets destroyed when black holes evaporate, breaking quantum mechanics, or the information somehow escapes, breaking our understanding of boundaries. Both options shatter fundamental physics principles that have never failed before. Scientists discovered that solving one physics problem creates an even worse disaster. To preserve information, some physicists propose that the boundary becomes a wall of high-energy particles hot enough to incinerate anything instantly. This firewall hypothesis suggests that quantum effects create a barrier of extreme radiation right at the boundary. Anyone falling toward it would be vaporized by particles carrying enormous energy before they could cross over. The firewall forms because of quantum entanglement breaking down at the boundary. That's a connection between particles that normally allows them to share information instantly across any distance. When this connection breaks, it releases devastating amounts of energy. This solution saves information but destroys the smooth boundary that relativity predicts. Falling observers would experience a violent death instead of crossing peacefully. The firewall trades one physics crisis for another equally serious problem. Two observers can witness the same event and experience completely incompatible versions of reality. This happens near cosmic boundaries where quantum mechanics and relativity create contradictory descriptions that cannot both be true. An outside observer sees information slowly leaking out through quantum radiation over millions of years. The information gets preserved in the radiation as required by quantum mechanics. Nothing dramatic happens at the boundary itself. Meanwhile, an infalling observer sees the information cross the boundary and disappear inside forever. From their perspective, the information definitely gets destroyed when the black hole eventually evaporates. The two observers reach opposite conclusions about the same physical process. Complementarity suggests that both descriptions remain valid in their own reference frames. The universe allows contradictory realities to coexist as long as the observers can never compare notes. This principle challenges our basic assumption that reality should be consistent for everyone. These cosmic boundaries might work like the ultimate data storage devices. All the three-dimensional information that falls inside could be perfectly encoded on the two-dimensional boundary surface itself. The holographic principle suggests that the boundary acts like a cosmic hard drive. Every bit of information about the interior gets written onto the surface in quantum-scale detail. The surface contains enough storage capacity to record everything that ever fell inside. Think of this like a hologram that stores three-dimensional images on flat surfaces. The boundary hologram stores all the information about the interior volume. The three-dimensional space inside becomes redundant because everything is recorded on the boundary. This principle resolves the information paradox by keeping all information accessible on the boundary surface. When the black hole evaporates, the stored information gets released with the quantum radiation. Nothing actually gets destroyed because everything was always recorded on the outside. quantum particles can remain mysteriously connected even when separated by cosmic boundaries. These quantum connections might be the key to understanding how information escapes from regions that trap everything else. Entanglement creates invisible links between particles that share quantum properties. When one particle changes its quantum state, its entangled partner appears to respond instantly regardless of the distance between them. This connection does not let you send messages faster than light, and it ignores normal space-time limitations in how the correlation shows up. Particles falling across the boundary remain entangled with particles outside. The boundary cannot break these quantum connections, even though it blocks all normal communication. The entangled particles on the outside carry information about their trapped partners. This quantum entanglement might provide a secret channel for information to escape. The trapped information doesn't need to cross back through the boundary. Instead, it flows out through quantum connections that exist outside normal space-time. The boundary blocks matter and energy, but may not fully stop quantum information transfer. The universe itself creates boundaries that permanently separate distant galaxies from each other. These cosmic barriers do not involve black holes or massive objects. Instead, the expansion of space itself generates regions that can never exchange information. Imagine galaxies racing away from each other as space expands between them. Some galaxies move away so fast that light from our galaxy can never catch up to reach them. The expanding space carries them beyond the reach of any signal we could ever send. This creates a cosmological event horizon around every observer in the universe. Beyond this boundary, galaxies become forever unreachable. We can still see light that left these distant galaxies billions of years ago, but we can never send messages back to them. The boundary grows larger as time passes, but new galaxies constantly cross it and disappear from our reachable universe. Space expansion creates the ultimate long-distance communication limit that affects every observer in the cosmos. Accelerate forever in one direction and you create your own personal event horizon. This boundary has nothing to do with massive objects warping space. Instead, constant acceleration generates a region behind you that becomes permanently inaccessible. This happens because of how acceleration affects your ability to receive information. As you accelerate faster and faster, signals from behind you get increasingly redshifted. Eventually, these signals become so redshifted that they can never catch up to you. Scientists call this a Rindler horizon after the physicist who first described it. The horizon forms a boundary surface behind any constantly accelerating observer. Light from beyond this surface can never reach the accelerating observer, no matter how long they wait. This effect works exactly like gravity near a black hole boundary, but with a crucial difference. The accelerating observer creates their own horizon by their motion. Turn off the acceleration and the horizon disappears, allowing communication to resume with previously unreachable regions. Future cosmic expansion will give every observer their own unique event horizon. This happens when dark energy dominates the universe and drives exponential expansion of space itself. Dark energy is a mysterious force that pushes space apart faster and faster over time. Scientists do not fully understand what causes it, but observations show it makes up most of the universe's total energy. This force will eventually overwhelm gravity everywhere. In this exponentially expanding universe, called de Sitter space, every observer develops their own personal boundary. The horizon surrounds each observer like an invisible sphere. Nothing beyond this sphere can ever send signals to the observer inside. This represents the ultimate future of cosmic isolation. Each observer becomes trapped in their own expanding bubble of space. They can never communicate with observers in other bubbles, even though both exist in the same universe. Can boundaries work in reverse, ejecting everything instead of trapping it? Mathematics predicts objects called white holes that function as exact opposites of black holes. These create boundaries where nothing can enter, but everything must exit. White holes represent time-reversed black holes in Einstein's equations. While black holes have boundaries where everything falls inward and nothing escapes, white holes have boundaries where everything flows outward and nothing can enter from outside. These reverse boundaries would violate causality in dramatic ways. Matter and energy would spontaneously appear at the boundary and shoot outward into space. The boundary acts like a cosmic fountain, spraying material in all directions without any apparent source. White holes probably do not exist in nature because they require perfect initial conditions that any small disturbance would destroy. However, the mathematical possibility shows that Einstein's equations allow boundaries that work in both directions, creating perfect sources instead of perfect sinks. Advanced civilizations might someday create their own event horizons using exotic matter and energy manipulation. These artificial boundaries would demonstrate complete mastery over space-time geometry itself. Warp drives require negative energy density to compress space in front of a spacecraft while expanding it behind. This extreme manipulation of space-time could accidentally create regions where the space-time curvature becomes so severe that artificial horizons form. Traversable wormholes also require exotic matter to keep their throats open for travel. The negative energy needed to stabilize a wormhole might create horizon-like boundaries where the wormhole connects to normal space. These boundaries could trap unwary travelers. Such technology would represent the ultimate engineering achievement, reshaping the fundamental structure of reality itself. Artificial horizons would prove that cosmic boundaries are not limited to natural objects but can be constructed by sufficiently advanced physics and technology. Empty space isn't actually empty. It constantly bubbles with virtual particle pairs that normally appear and disappear instantly. Near cosmic boundaries, something extraordinary disrupts this quantum dance and turns virtual particles into real ones that can escape forever. Quantum mechanics tells us that empty vacuum space contains endless energy fluctuations. These fluctuations constantly create pairs of particles and antiparticles that exist for tiny fractions of a second before annihilating each other back into nothing. Near the boundary, the extreme gravitational field tears these particle pairs apart before they can destroy each other. One particle falls across the boundary and becomes trapped inside forever. Its partner escapes outward into space as real radiation. This process slowly drains energy from the black hole because the escaping particle carries positive energy, while its trapped partner carries negative energy. The boundary acts like a cosmic particle accelerator, converting virtual quantum fluctuations into actual radiation that streams away into space. What if the smallest furnaces burned the hottest while giant ones stayed ice cold? Black holes follow exactly this backwards rule. The more massive they become, the colder their temperature gets. A black hole with our sun's mass radiates at an incredibly tiny temperature. Its thermal radiation would be millions of times colder than empty space itself. You'd need sensitive instruments to detect any heat at all coming from these cosmic giants. Meanwhile, microscopic black holes would glow white hot with temperatures hotter than stellar cores. A black hole the size of a proton would radiate at billions of degrees. These tiny objects would shine brighter than any star. This inverse relationship happens because smaller boundaries have stronger surface gravity. Surface gravity determines the temperature of the quantum radiation. The stronger the surface gravity, the hotter the thermal glow that emerges from the boundary region. Scientists discovered something impossible about these cosmic boundaries. The amount of information they can hide doesn't depend on their volume like normal storage devices. Instead, it depends only on their surface area. Think of information storage in normal objects. A hard drive's capacity depends on how much volume it contains inside. Double the size and you can store roughly twice as much data. This volume rule applies to every information storage system humans have ever built. Black hole boundaries break this rule completely. Their information storage capacity depends only on their surface area, not their interior volume. Double the surface area, and you double the maximum information that can be hidden inside. This area law reveals something profound about the nature of information itself. The boundary surface acts like a cosmic hard drive where every square unit of area stores a fixed amount of information. This discovery led to the holographic principle that suggests our three-dimensional reality might be encoded on a two-dimensional surface. The smaller a black hole gets, the faster it evaporates. This creates a runaway process that ends in a spectacular explosion when the black hole finally disappears completely from the universe. Here's how the death spiral works. Small black holes radiate at higher temperatures than large ones. Higher temperature means more energy gets radiated away per second. As the black hole loses mass through radiation, it shrinks and gets even hotter. This feedback loop accelerates over time. The black hole radiates faster as it shrinks, which makes it shrink even faster, which makes it radiate faster still. What starts as an imperceptibly slow evaporation becomes a runaway explosion. A black hole with our sun's mass would take longer than the age of the universe to evaporate completely. But in its final second, it would release as much energy as millions of hydrogen bombs exploding simultaneously. The universe's ultimate fadeaway becomes its most violent finale. Gravity behaves exactly like heat in ways that shouldn't be possible. The laws that govern cosmic boundaries match the laws of thermodynamics with mathematical precision, as if these two completely different phenomena are secretly the same thing. The first law of thermodynamics says energy can never be created or destroyed, only transformed. Black hole mechanics follows an identical law where mass, angular momentum, and electric charge are conserved in all interactions. The second law of thermodynamics says entropy always increases in isolated systems. Black hole mechanics obeys a parallel law where boundary area always increases when black holes merge or absorb matter. This perfect correspondence suggests something deeper about the nature of gravity itself. Perhaps gravitational effects and thermal effects are two different ways of describing the same underlying physics. The cosmic boundaries reveal that information, entropy, and space-time geometry are all connected at the most fundamental level of reality. Space around rotating black holes moves like thick honey being stirred by a cosmic spoon. The spinning boundary doesn't just sit there passively. It grabs the fabric of space-time itself and forces everything nearby to rotate along with it. This effect is called frame dragging because the rotating mass literally drags the reference frame of space and time. Even if you fire your rockets to remain perfectly stationary, the spinning space-time pulls you around in circles against your will. Scientists call the region where this happens the ergosphere. That's the technical term for the zone outside the boundary where nothing can remain at rest. Your rockets might work perfectly, but space itself moves beneath you like a cosmic treadmill. The faster the black hole spins, the stronger this dragging effect becomes. Near maximum rotation, the ergosphere extends far beyond the boundary itself. Space becomes a whirling maelstrom that forces everything to participate in its eternal dance, whether they want to or not. Throw something into a spinning black hole, and you might get back more energy than you put in. This seems to violate conservation of energy, but it actually represents the universe's most efficient power generation scheme ever discovered. The trick involves sending a particle into the ergosphere and splitting it into two pieces at just the right moment. One piece falls across the boundary carrying negative energy. Its partner escapes outward, carrying more positive energy than the original particle had. This process is called the Penrose mechanism, after the physicist who discovered it. The escaping particle steals rotational energy from the black hole itself. The spinning boundary slows down slightly, while the particle gains extra energy seemingly from nowhere. You could theoretically extract enormous amounts of energy this way until the black hole stops spinning completely. The rotating boundary acts like a cosmic battery that stores the energy of rotation. The Penrose process provides a way to tap into this ultimate power source. Matter falling toward these boundaries cannot simply spiral inward like water going down a drain. Instead, it gets compressed and heated to such extreme temperatures that powerful jets of particles blast outward at nearly the speed of light. The infalling material forms what scientists call an accretion disk. That's the technical term for a flat, rotating disk of superheated matter that gradually spirals inward toward the boundary. Friction within this disk generates temperatures of millions of degrees. These extreme conditions cannot be contained within the disk itself. The superheated material breaks free from the disk's gravitational grip and shoots outward in two narrow jets perpendicular to the disk. These jets stretch for thousands of light years across space. The jets carry away enormous amounts of energy and momentum that would otherwise fall into the black hole. This process makes the boundary region one of the most efficient energy converters in the universe, turning gravitational potential energy into directed streams of high-speed particles. Two massive black holes circling each other should merge silently since nothing can escape their combined boundaries. Instead, their collision creates the loudest sounds the universe can make, ringing space-time itself like a gigantic bell. These sounds aren't made of air vibrations that our ears could hear. They're made of space-time vibrations called gravitational waves. When black holes spiral into each other, they create ripples in the fabric of reality itself that spread outward at the speed of light. The final moment of merger, for a brief moment, releases more power in gravitational waves than all the stars in the observable universe produce in light. This energy gets radiated away as pure geometry, stretching and compressing space itself as the waves pass through. Advanced detectors like Luojuo can measure these space-time ripples by detecting tiny changes in distance as the waves pass Earth. The detectors reveal that merging black holes create characteristic chirping sounds as they spiral together, turning the most violent events in space into an alien form of cosmic music. What if quantum mechanics provides a secret escape route from regions that trap everything classically? Quantum tunneling allows particles to appear on the other side of barriers that should be completely impassable according to normal physics. In quantum mechanics, particles behave like probability waves that can leak through barriers even when they lack sufficient energy to climb over them. This tunneling effect works for everyday barriers like the walls inside electronic devices. Near cosmic boundaries, quantum tunneling might allow particles to escape from inside the boundary back to the outside universe. The boundary acts like an extremely thick quantum barrier that classical physics says nothing can penetrate from inside. However, quantum probability waves could theoretically tunnel through this barrier and allow particles to materialize outside the boundary. This quantum tunneling provides the microscopic mechanism that creates Hawking radiation, turning the ultimate classical trap into a quantum leaky container that slowly evaporates over time. You cannot photograph something that emits no light. Cosmic boundaries remain completely invisible because nothing can escape from them to reach our telescopes. Yet scientists found a way to capture images of these unseeable barriers by photographing their shadows. The Event Horizon Telescope represents humanity's most ambitious astronomical project. This telescope isn't a single instrument, but a network of radio dishes scattered across the entire planet. When synchronized together, they create a virtual telescope the size of Earth itself. This planetary telescope can detect the shadow that a cosmic boundary casts against the bright material swirling around it. The boundary appears as a dark circle surrounded by glowing hot matter. It's like seeing the silhouette of an invisible person standing in front of a bonfire. The first image of a cosmic boundary shadow revealed a dark ring exactly matching theoretical predictions. The shadow photography technique transforms completely invisible objects into observable silhouettes, allowing us to study the universe's most hidden structures through the absence of light rather than its presence. Massive objects warp space-time so severely that they transform into cosmic magnifying glasses. Light from distant sources gets bent around these invisible lenses, creating multiple distorted images of the same background object. This effect works like looking at something through the bottom of a curved glass. The lens bends light rays and can create multiple images or stretched arcs of light. Cosmic boundaries act as perfect spherical lenses that focus light in characteristic patterns. Scientists call this gravitational lensing because massive objects lens light through pure geometry rather than glass or mirrors. The more massive the object, the stronger its lensing effect becomes. Cosmic boundaries create some of the most extreme lensing in the universe. When astronomers see perfect Einstein rings or highly distorted multiple images, they know a massive invisible object sits between them and the background light source. The lensing patterns reveal the mass and location of cosmic boundaries that remain completely invisible to direct observation. X-ray telescopes can follow superheated matter as it spirals toward cosmic boundaries. The material glows brighter and hotter as it approaches the point of no return. Then it simply disappears from all observations at a specific distance from the invisible center. This vanishing act provides crucial evidence for the existence of these boundaries. Normal massive objects like stars would reflect or absorb the infalling material. Only objects with boundaries that trap everything permanently could make matter disappear so completely. The disappearing matter creates what scientists call the innermost stable circular orbit. That's the technical term for the last possible orbit around a cosmic boundary before matter must fall across the point of no return. X-ray observations reveal that matter follows stable orbits down to this critical radius, then vanishes forever within a few orbits. This sudden disappearance at a precise distance matches theoretical predictions for cosmic boundaries with mathematical precision, providing indirect proof of their existence. When two cosmic boundaries merge together, they create the most violent explosion possible in the universe. Yet this explosion produces no light that any telescope can detect. Instead, it rings space-time itself like a cosmic bell that scientists can hear with gravitational wave detectors. These detectors use laser beams to measure incredibly tiny changes in distance caused by passing gravitational waves. When space-time ripples pass through Earth, they stretch and squeeze the detector arms by amounts smaller than a proton. The final moment of boundary merger creates a characteristic signal called ringdown. That's the technical term for how the newly formed boundary settles into its final shape, like a struck bell gradually stopping its vibrations. This ringdown signal encodes information about the size, mass, and rotation rate of the newly formed boundary. By analyzing these space-time vibrations, scientists can determine the properties of cosmic boundaries that formed in the most energetic events the universe can produce, revealing details about objects that emit no light whatsoever. Stars orbiting near cosmic boundaries move so fast that they test Einstein's theory of relativity with every orbit. Their paths reveal tiny deviations from Newton's laws that only occur in the most extreme gravitational fields the universe can create. Near the center of our galaxy, astronomers track individual stars as they complete elliptical orbits around a massive invisible object. These stars reach speeds of thousands of miles per second at their closest approach to the central mass. At these extreme speeds, relativistic effects become measurable. The star's orbit precesses slightly with each passage, rotating like a cosmic rosette. This precession matches Einstein's predictions for objects orbiting near cosmic boundaries. The stellar orbits also experience gravitational redshift as they climb out of the deep gravitational well. Light from the stars gets stretched to longer wavelengths as it escapes the intense gravity. These combined relativistic effects confirm that the central object must be a cosmic boundary rather than any normal type of massive star or cluster. Our current understanding of cosmic boundaries might be completely wrong at the smallest scales imaginable. At distances far teenier than atoms, space and time themselves might bubble and foam like quantum sea spray, fundamentally changing what these boundaries actually mean. Scientists call this microscopic scale the Planck length. That's the technical term for the smallest meaningful distance in physics, where quantum effects become so strong they reshape the very fabric of space-time itself. At this scale, the smooth boundaries we've been discussing might break down into a chaotic quantum foam. Space-time could be constantly fluctuating, creating and destroying tiny virtual boundaries that pop in and out of existence faster than any measurement could detect. This quantum foam could mean that sharp, well-defined boundaries don't actually exist at the fundamental level. Instead, they might be approximate descriptions that only work when we ignore the violent quantum activity happening at microscopic scales. The universe's most absolute barriers might turn out to be fuzzy quantum approximations. Could the most fundamental structures in space be one-dimensional vibrating strings rather than point particles? String theory suggests that cosmic boundaries might emerge from complex interactions between these microscopic vibrating entities. In string theory, everything in the universe consists of incredibly tiny loops of energy that vibrate in different patterns. Different vibration modes create different particles, like cosmic musical notes that determine the properties of matter and energy. Scientists call special string configurations D-branes. These are surfaces where strings can stick and interact with each other. Some physicists think cosmic boundaries might be enormous D-branes made of countless strings vibrating in perfect coordination. If this theory proves correct, the sharp boundaries we observe are actually collective behavior of trillions of microscopic strings. The boundary emerges when strings organize themselves into stable patterns that trap matter and energy. String theory transforms cosmic boundaries from geometric features into dynamic quantum orchestras. Imagine space-time built from discrete quantum pixels rather than smooth continuous fabric. Loop quantum gravity proposes that boundaries exist in a fundamentally granular universe where space itself comes in smallest possible units. This theory suggests that space-time has an atomic structure made of quantum loops woven together into a cosmic network. Just like matter is made of atoms, space itself might be constructed from indivisible quantum building blocks. At cosmic boundaries, this quantum geometry creates special quantum states that don't exist in classical physics. The boundary becomes a quantum interface between different regions of granular space-time rather than a smooth mathematical surface. These quantum boundaries would have properties that classical physics cannot predict or explain. They might allow limited communication across the boundary through quantum entanglement between the space-time atoms. The universe's most absolute barriers might have quantum loopholes built into their fundamental structure. Physics faces an impossible limitation when studying cosmic boundaries directly. We cannot send probes inside to report back what they find. However, holographic duality offers an unexpected solution by solving three-dimensional boundary physics using two-dimensional mathematics. This approach treats cosmic boundaries like cosmic holograms that encode all interior information on their two-dimensional surfaces. Instead of studying the mysterious three-dimensional interior, physicists can analyze the boundary surface using well-understood mathematical techniques. The holographic method has already solved problems that seemed impossibly complex using traditional approaches. Calculations that would take centuries using three-dimensional methods become manageable when translated into two-dimensional boundary theories. This dimensional reduction might be the key to understanding everything about cosmic boundaries without ever crossing them. The most complex three-dimensional physics problems transform into solvable two-dimensional puzzles, opening entirely new ways to probe the universe's most inaccessible regions. Recent theoretical work suggests that cosmic boundaries might not be dead ends but doorways to entirely separate universes. What disappears across these boundaries might not be destroyed, but transported to baby universes that branch off from our own reality. This possibility emerges from equations that describe what happens to space-time geometry near cosmic boundaries. Under certain conditions, the equations allow space-time to pinch off and form isolated bubble universes connected to the original boundary. These baby universes would be completely separate realities with their own space-time and physical laws. Matter crossing the boundary might continue existing in these parallel domains, invisible and unreachable from our universe, but very real in their own right. If this theory proves correct, cosmic boundaries become cosmic birthing centers where new universes constantly split off from existing ones. The universe's most absolute isolation barriers might actually be the most prolific creators of new realities, transforming cosmic death into cosmic reproduction.